So now what I want to do is H map 0 to plus and vice versa, and H maps 1 to minus and vice versa. So what H does for the Hadamard matrix is it takes the 0, 1 bases to the plus minus bases. So now let's remember our entangled state that I wrote down. One over root 2, 0, 1, minus 1, 0. So what does it look like in plus minus basis? Well, what we can do is we can write this as a vector and then use this H tensor H transformation that we did. So writing it as a vector, 0, 0, 0, 1, 1, 0, 1, 1 is just 0, 1 over root 2, minus 1 over root 2, 0. 0, 1 over root 2, minus 1 over root 2, 0. So H tensor H times 0, 1 minus 1, 0 over root 2 is equal to, well, the top vector, or rather, the top row is orthogonal to this, so that's 0 times plus plus, because remember, this is changing the basis. The next row is minus 1 over root 2 times plus minus, plus 1 over root 2 minus plus, plus 0 minus minus. So that means 1 over root 2, 0, 1 minus 1, 0 is equal to minus 1 over root 2 plus minus 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 plus. So this state, which was entangled in the 0, 1 basis, is essentially the same entangled state with a global phase in the plus minus basis. So what we've done is we've rotated both. Well, you can think of this as either changing the basis on both qubits or rotating both qubits. But either way, we get the same state. And there's a remarkable fact about this state. Okay, so
shouldn't that equality be written with the Hadamard in front?
no. because, 0, 1 minus 1, 0 is equal to Hadamard minus Hadamard times 1 over root 2, 0, 1 minus 1, 0. So this is certainly true. But what the Hadamard does is it changes the basis from 0, 1 to plus minus. So if you write this as 0, 1 minus 1, 0 and plus, remember plus was equal to 1 over root 2, 0 plus 1, and minus was 1 over root 2, 0 minus 1. So if you just substitute this in here, you will get this. Because what the Hadamard does when applied to 0, 1 is turn 0 into plus and 1 to minus. So this is a legitimate equality, and this is also a legitimate equality. Maybe I should write this out. Yeah, maybe I should just expand this to show you that it's really true. Minus 1 over root 2 plus was 0 plus 1, and minus was 0 minus 1. And we have another 1 over root 2. Well, we have 1 over root 2's because minus 0 minus 1, 0 plus 1. So we have a 1 over root 2 from here, and two 1 over root 2's from this guy and this guy. So that's minus 1 over 2 root 2. And here we get 0, 0, minus 0, 0. Here we get minus 0, 1, minus 0, 1, root 2, 0, 1. And here we get, well, the 1, 1's cancel, and the 1, 0, and the 1, 0 add up, and they both have plus signs on them. So you get a plus 2, 1, 0. OK, why don't I just do it that way? So when you multiply these things out, you get this, which gives you that equals that. Right, because I forgot that minus sign. So there's a 0, 1, minus 0, 1 on the inside. There was a minus sign on the front. From here, that equals that. So the Hadamard matrix is changing the basis from 0 to plus and 1 to minus. And I really should write Hadamard tensor product with itself because we're applying the Hadamard to both qubits. OK. So tensor products are one of the most confusing things about this course. So are there any questions about them? Yeah?
Is there any way to apply a single qubit gate to one of the qubits without having to compute a tensor product?
Yeah, there is. So I mean, maybe I should do an example. Because, yeah, you don't really want to compute tensor products. So what you can do is you can let's apply h on the first qubit of 0, 0 plus 1, 1. where this is AB, AB. We know h of 0 equals 1 over root 2, 0 plus 1. So we can apply the Hadamard. And actually, technically, what we're doing is applying the Hadamard tensor of the identity to this. If you want to make sure all your dimensions add up to the matrices, but quite often we'll just apply, say, we'll just use this notation, and we'll leave the tensor of the identity, implicit. So if you apply the Hadamard to the 0, you get 0 plus 1 A, 0 B, and maybe I should put a tensor product in, plus 0 minus 1 A, 1 B is equal to 0, 0 AB So we have a 0, 0. And now the next one, if we're writing them in lexicographic order, is 0, 1 plus 0, 1 AB plus 1, 0, 1, 0 AB minus 1, 1 AB. So you just apply HA to this qubit and leave all the other qubits in this expansion alone. And you get this. And that's much better than, or much more efficient than taking the tensor product of H with the identity and then multiplying it out. Any other questions? Yeah?
Is every transformation that you can apply to multiple qubits necessarily a tensor product of unitary matrices?
No. Every transformation you can apply to multiple qubits is a what? It's a unitary matrix, but it's not necessarily a tensor product. In fact, if everything was a tensor product, then you couldn't really do quantum computation, because if you start with a tensor product of qubits and apply tensor products, I apply tensor product unitary to each of them, I mean, a string of tensor product unitaries to them, you'll never get qubit 1 to talk to qubit 2. And to do quantum computation, you really need qubit 1 to talk to qubit 2.